Hi, I'm Suyang. We introduce SIDL, a new dataset for restoring smartphone images with dirty lenses. This was conducted at Chungji University with Professor Hyun Kim. As we all know, smartphone cameras are essential in everyday life. They are used in various places and situations. However, their lenses are often exposed to contaminants such as dirty particles, scratches, fingerprints, and water drops. These factors significantly degrade image quality, affecting the quality of our everyday photos. So, can current restoration models effectively handle lens contamination problems? We tested how well current state-of-the-art restoration models can restore images degraded by lens contamination. Despite their advanced capabilities, current SOTA methods struggle to handle the diverse and complex degradation patterns caused by lens contamination. Furthermore, generative models not tailored to specific datasets, such as AAAI, also failed to produce satisfactory results. Why do current methods struggle with lens contamination? Addressing this challenge is expected to require diverse efforts beyond network design. To advance research in this field, it is essential to evaluate and analyze existing methods to guide future directions. And the first step is to create datasets that capture the complexity of lens contamination in real-world scenarios. Previous image restoration research has introduced numerous datasets to address various types of image degradation and environmental conditions. These datasets cover traditional tasks like deep learning, denoising, as well as environmental factors such as haze and low light scenarios. For the dirty lens problem, two datasets have been introduced. Wang et al. Provides only single degradation type scratches. Let's see clearly created synthetic degradation patterns. Both data tests do not provide raw data. So we can see that existing dirty lens datasets are limited scope. This lack of comprehensive real-world lens contamination data creates a significant research gap, making it difficult to develop effective restoration methods. To bridge this research gap, we propose smartphone images with dirty lenses called SIDL, a dataset for learning and evaluating the restoration of images captured by contaminated smartphone camera lenses. SIDL offers a diverse collection of real-world images taken in various lighting conditions and environments with common lens contaminants, including water drop, fingerprint, dust, scratch, and the mixture of contaminant types for 300 scenes, resulting 1588 images. Let's first consider the general process of image acquisition. Light from the rear scene passes through the lens and reaches the sensor. The sensor converts this light into a clear digital image. This is the general smartphone image capture process. However, to obtain these degraded images, directly damaging the lens is impractical and expensive. Then, how can we effectively replicate real-world contamination during the image acquisition process without physically damaging the lens? To address this challenge, we introduce our SIDL capture process. Instead of damaging the lens directly, we use very thin films. Then we create various types of damage on these films. This film is placed in front of the lens, simulating real-world contamination. When light passes through this dirty film, it creates realistic scratching and distortion effects. These effects replicate the effect of real-world lens contamination and result in degraded digital images. This approach allows us to create a diverse range of contamination scenarios for the SIDL dataset. To capture images under controlled conditions for SIDL dataset, we developed our image acquisition setup. First, we designed a custom film holder using Maya 3D modeling software. Next, using a 3D printer, we created the physical film holder. This holder maintains consistent placement of contaminated films in front of the camera lens. To this end, we integrated this holder with a smartphone mount for the complete setup. To simulate real-world lens contamination, we created various dirty films including dust, fingerprints, water drops, and scratches. Additionally, we combined different types of degradations to create mixed patterns that better represent real-world scenarios. Furthermore, reusing dirty films for multiple scenes could lead to models memorizing specific patterns. To prevent this, we captured new dirty films for each scene. The SIDL dataset is constructed with 300 scenes for each type of degradation, split into 240 for training, 20 for validation, and 40 for testing. To ensure real-world applicability, we carefully designed our dataset to cover various environmental conditions. The scenes include both day and nighttime periods, indoor and outdoor locations, and different levels of artificial lighting intensity from high to low. Additionally, for evaluation, we categorized images into 3 difficult levels: easy, medium, and hard based on PSNR values. We conducted experiments on the SIDL dataset using state-of-the-art network architectures, employing both all-in-one and task-specific training strategies depending on the model. As shown in the table, DeepUIR outperforms other methods across most degradation types and difficulty levels. However, the qualitative results are unsatisfactory and present a severe degradation, requiring breakthroughs in the follow-up studies. This evaluation study presents that our SIDL dataset closely replicates real-world degradation patterns. All real images and their restoration results exhibit similar characteristics to those of SIDL images. Next, we compared the pre-trained models with SIDL-trained models for water and dust cases. The results clearly show that models trained on our SIDL dataset significantly outperform pre-trained models, demonstrating the unique characteristics of our degradation patterns. We also compared NAFNet models trained on different dirty lens datasets. The results show that our SIDL trained model performs better than one et al. Dataset across all difficulty levels, especially in challenging conditions. To summarize our work, first, SIDL provides a realistic dataset of 1588 image pairs specifically designed for smartphone lens contamination restoration. Second, our extensive experiments validate that SIDL effectively represent real-world lens contamination problems. Lastly, SIDL will be a valuable benchmark for developing better restoration methods for everyday smartphone camera problems. We hope SIDL leads to diverse future research in this underexplored area of image restoration. For more details about our work, including online evaluation, baseline code, and access to the dataset, please visit our website. Thank you.